Okay, we're going to continue our lesson on connectivity of digraphs now with a couple more theorems that are going to kind of better illuminate the connectivity nature of digraphs. It's never going to be quite so simple as connected components in an undirected graph, but it's a more complicated structure, and we'll sort of tease out that structure a little better with what we're going to do next. So should remember or have in your head a couple of the definitions from the previous lesson. Again, a digraph is strongly connected if it has the property that for any vertex u and for any vertex v, there's a directed walk from u to v. If I give you a digraph D, we have a notion of a strong component. So a strong component is going to be a maximal, strongly connected subdigraph. And what's true in digraphs with the strong components is very similar to what's true in ordinary undirected graphs for the components. Namely, each vertex of the digraph is contained in a unique strong component. And whenever you look at the strong components for any two vertices within that strong component, just within that strong component, there will be a walk from u to v and a walk from v to u. So the strong components are kind of answering the question, suppose I have two vertices and I want to know if there's a walk from say, u to v and also v to u. So the answer to that question is if and only if u and v are in the same strong component. And that feature will help you to kind of find these things. If you say two vertices, u and v, and you can find a walk from u to v and a walk from v back to u, then those two are in the same component. Or even more generally, if you just start at some vertex and you can find a closed walk, if you can go out and come back, then all the other vertices on that closed walk have to be in the same strong component as u, because just walking around that closed walk, you can start at any vertex and go to any other, moving only in the forward direction. And so that's a kind of if and only if that will allow you to actually form these things, right? So you can see in my strong components, I mean, most of these many of them are just a single directed cycle. Some of them are single vertices. You see one over here on the sort of lower and to the left that it's not a single directed cycle, but it's a union of two directed cycles meeting at a vertex. It is easy to see that all those vertices have to be in the same strong component because you have a closed walk that contains all that stuff. Now, what you'll see when you do look at this picture is that apart from the strong components, all the edges are actually directed downward, right? And that fact makes it easier to understand why these things are the strong components, why we don't have anything more. You can kind of, I mean, in principle, you could sort of run along and say, well, is there another closed walk? I can see that I can get from this vertex to this vertex in the digraph. Is it possible you can get back and try to argue it case by case? Again, we have a theorem that says if you pick any pair of vertices in the whole digraph, say u and v, either there's a directed walk from u to v, or there's a good reason why not. Namely, you can find an edge cut so that it's clear you can't get from u to v because with the for this edge cut, all the edges go the wrong way, right? So u is stuck on one side, v is stuck on the other side, and all the edges go the wrong way, so you just can't get u to v. But what we're seeing in this picture is kind of a very helpful feature here, and it's this kind of downward orientation of the edges, right? And so we can see here that these in fact are the strong components for the reason that if you look at any two of these other strong components, you're going to see a cut that stops you, and you can see the cuts very clearly because of this kind of vertical orientation. In fact, kind of all of the edges are sort of going down in this picture, and I could have made this even more extreme. In fact, you can even sort these strong components linearly. So just in a line so that all of the edges are directed down. And that makes it especially clear that, you can't get from a lower vertex to a higher vertex. And in fact, that's the structure that we're going to be kind of teasing out. So, right. So Again, we have a somewhat more general looking example. These are the strong components. Again, these are not terribly hard to form. For two vertices, they're going to be in the same strong component if and only if there's a directed walk this way and also that way. You can use that and slowly find these things. Now, what we're seeing again in this picture is that if you're looking at the edges outside of the strong components, they're all kind of directed downward in the picture. And so if you have a vertex that's lower, you just have no hope of getting up to a vertex that's higher. Now, I want to say conversely, it's not that the higher vertices necessarily connect to the lower ones. For instance, if you look at this top component here and this component down here, well, this upper green arrow is pointing to a component up top, and this lower green arrow is pointing to a lower one. Now, you certainly can't get from the lower one to the higher one because there's just no way of going up in the picture. All of my directed edges are always directed down. But in this case, you can't get from the higher one down to the lower one. So sometimes you can get from a higher one to a lower one. You could get from that top one down to, say, this one. That's not that you can do. You can follow along some edges and get down there, but you can't get to that one over on the other side. So when we're talking about directed walks from U to V, strong components are nice because they tell me when you have walks both ways. This picture, the orientation of this picture is nice because it's going to tell us something. It's going to tell us a whole lot of things are forbidden. If you have a lower one, you can't get up to a higher one. But we're leaving something a little less clear. For a higher one, you might or might not be able to get to a lower one. And that's kind of the structure that we're going to end up with in the end. So this is why I was saying the digraph connectivity is really a step more subtle than graph connectivity. If you just have an undirected graph, you've got some connected components, and if you want to know, is there a walk from U to V, the question is equivalent to, are they in the same connected component? And that's the end of the story. Here, that's gotten to be just a bit more complex. But there is a lot to know about this, and we do want to get the basic theorems that are going to allow. So we already know that every vertex is in a unique strong component. We now want to get some theorems that help us to kind of arrange these strong components so we have this kind of notion of downward. And as I say, it's not a complete answer to the question, but it's going to be kind of the best we've got, and it is a useful answer, even though it's not it's maybe not everything there is to know here. Okay, so let me leave this example on the side now and go on to introduce our next theorem. So our first lemma here is going to be a condition that's going to imply that a directed graph has a directed cycle, and this is a fairly simple one. It's actually really in analogy with something we did for the undirected case. So let me just put the statement up. If every vertex of D has out degree at least one, then D contains a directed cycle. Right. We had a lemma for undirected graphs saying if you have an undirected graph and every vertex has degree at least 2, then you're guaranteed the presence of a cycle. And this is very much in analogy with that fact, and the proof is almost exactly the same. So we proved that theorem by choosing a maximal path in our graph. Now we're going to choose a maximal directed path. So let's choose a maximal directed path P with, let's say, in fact, I don't even need to name it. I'll just say V, let me say V1, E1, V2 on up to EK, VK plus 1. So I don't know why I'm not drawing this in picture form. Okay, so there's my maximal directed path. Now, again, the main thing you know about a maximal directed path, the only thing you know about a maximal directed path is that you can't make it longer. So what does that mean? That means that if you start at the vertex v sub k plus 1 and try to walk out along any directed edge, you're going to have to come back to a vertex that you've already used. Otherwise, this path wasn't maximal. Same thing at the vertex v1. If you wanted to go backward along an edge, if you wanted to find some vertex that has an edge from it to v1, again, that vertex had better lie on this path already. Otherwise, it wasn't maximal. Now, what do we know about our digraph? We know that every vertex has out degree at least 1. So I know that the degree of the vertex vk plus 1, the out degree is at least 1. That means there's an edge that goes from vk plus 1 to some other vertex. Again, by maximality, that vertex must lie along the path. So since the path is maximal, this means there must be an edge of the form vk plus 1, say vi, in my digraph. Again, I know there's some edge that goes from vk plus 1 to some other vertex. By the maximality of the path, that other vertex had better also lie on this path, and that gives me an edge of this form. And now I'll just draw it over here. So we get an edge that looks like this. And now I'm going to find a directed cycle using the vertices vi up to vk plus 1. And I'll just sort of say that. Now, in fact, now I'll just say now the path together with this edge contains a directed cycle. That completes the proof. Yeah, and I should say, maybe I don't need to say it again, but I will. This is just like the undirected setting. So again, in the undirected case, if you had a graph where every vertex has degree at least 2, you were guaranteed the presence of a cycle. The proof is you take a maximal path and you just pick on either end. For either end, its degree is at least 2, and that means there's another edge sticking out of that vertex. Because your path is maximal, it can't go anywhere new, and that means it has to circle back, and that gave you a cycle. So same exact argument, same basic result here. So if you have a digraph and every vertex has out degree at least 1, you are guaranteed that that digraph will contain a directed cycle. Okay, on to a key definition. We call a digraph acyclic if it has no directed cycle. So, right, when we were in the setting of graphs, when you're looking at graphs that have no cycle, of course, those are forests, and we understand their structure. It's really quite simple. In the digraph setting, acyclic digraphs can be richer objects. So just sort of as a warning, but anyway, we have a nice term for them. A digraph is acyclic if it has no directed cycle. Now, and let me just point out what our previous lemma says in this context. Our previous lemma says, well, our previous lemma, the forward direction of it says if you have a digraph where every vertex has out degree at least 1, then you have a directed cycle. But what's the contrapositive? That means if you do not have a directed cycle, that means if your digraph is acyclic, it must have a vertex of out degree 0. And similarly, I mean, you can just turn all the edges around and apply the same fact, and it will tell you that if you have an acyclic digraph, you must also have a vertex within degree 0. Sometimes we call those things sources or sinks. So you think of a vertex as a source if the only edges go out of it, and as a sink if all the incident edges are directed toward it. So again, that previous lemma that we just proved said in the contrapositive, which is how we'll be applying it, it's telling us that every acyclic digraph has a sink and every acyclic digraph has a source. And that's going to be the key idea in the proof of the following proposition. This is not a particularly deep thing when you see it, but it is the thing that's going to give us our nice structure. So a digraph D is acyclic if and only if you can order the vertices V1 up to Vn so that all the edges go left to right. My previous one I had edges kind of going down. This is the same the same phenomena, but now just for sort of typographical, or I should say just for sort of logistic reasons, I'm going to lay things out left to right. Let me get the statement of this proposition up. So D is acyclic if and only if there's an ordering of the vertices V1, V2 on up to Vn, so that every edge Vi, Vj satisfies I is less than j. Right? So again, what we're saying here is that your digraph D is acyclic if and only if you can put the vertices in order, V1, V2 on up to Vn, in such a way that all of the edges go left to right. So every possible edge that you see here, if there's an edge from between with ends V2 and V4, then it has to be directed from V2 to V4, right? So all of the edges in this picture go to the right. This picture should make it clear that certainly a digraph with this feature cannot possibly have a directed cycle. It doesn't have even a closed direct walk with positive length, because if you start at a vertex and start walking, you go strictly to the right and you can never come back, right? So what's going to go on is that certainly if you have a digraph with this feature that you can order the vertices V1 up to Vn so that all of the edges go left to right, well, then it certainly does not have a directed cycle. We need to prove the other direction. Suppose you have a digraph which is acyclic, then let's see that it has this this ordering. So so the if direction is, I'll just say it's immediate. Again, if you can order the vertices like this, it's very clear that you do not have a directed cycle, because if you start at a vertex and start walking out from that vertex along an edge, you will only go to the right in this graph, and you can never get back to where you started. So the if direction is just that. For the only if direction, we're going to go by induction. So the only if will be induction on the number of vertices. As a base case, I'll say if the V of D is 1. If you have one vertex, then it's very clear that this must be true. If I give you a one vertex digraph and it's acyclic, that means you don't have you better not have a loop, right? A one vertex one vertex with a loop at that vertex, that is a directed cycle. I'm telling, our input assumption here is that our digraph is acyclic. So if I'm giving you a one vertex digraph that is acyclic, it will have no edges whatsoever, and that the trivial ordering will satisfy this property. Right? I give you just the vertex v. Well, it is true that for every possible edge, it goes left to right in the picture because there are no edges. So in this case, if you have one vertex, then d, in this case, since d is acyclic, it has no edges. Oops. So there are no edges, and the trivial ordering works. Okay, so our base case is done. Now I'm giving you a graph. So now for the inductive step. So now we have a graph with at least two vertices. So now I know that the number of vertices of D is at least 2, and I know that this statement holds true by induction. So for any graph with fewer than n vertices that is acyclic, we are going to have this property. But I want to pick a good vertex to delete, and now's where this observation from the previous lemma comes into play. Again, the previous lemma, I proved it in the forward direction. If every vertex has out degree at least 1, then you have a directed cycle. But the contrapositive says that if you have an acyclic digraph, there is a vertex without degree 0. So by the lemma, we may choose a vertex v such that the out degree of v is 0. And that's a really nice vertex, right? That's a vertex that we can put at the end. That's a vertex that we can put all the way to the right. In fact, I know I'm going to put it at the end. Let me call it v sub n. I'll choose a vertex v sub n whose out degree is equal to 0. That's a perfectly good vertex to put as the very last one in our list, because all of the edges that have that vertex as an end, well, they're directed toward it. So that's a perfect vertex to go last. And now you see what we will do. I will delete the vertex vn from the digraph. That digraph will be acyclic. You better not have a directed cycle there, right? Because the original digraph is. And that means that this smaller digraph by induction is going to have a suitable ordering. And I put v sub n at the end. And that's the whole proof. I will write a little bit more of that. So now by induction, d minus v sub n has an ordering, say v1 on up to vn minus 1, with all edges to the right. And now the ordering v1 up to vn minus 1 vn is a suitable ordering of the original. Now that ordering has the desired properties. Again, we know that every edge not incident with Vn is going from left to right in that ordering by induction. We know that all of the edges that are incident with Vn go from some other vertex to v sub n, so it works for those edges too, and that's completing our proof. Right, so this is not by any means a complete story, but it is a very, very useful tool. Again, if a digraph is acyclic, this means that you can order the vertices so that all of the edges go downward, or if I keep swapping back and forth between horizontal and vertical orientation here. If a digraph is acyclic, then you can order the vertices v1 up to vn so that all of the edges are directed left to right in this picture. And vice versa. If you have a digraph with this kind of linear ordering and all edges going left to right, then you will be acyclic. So this is a necessary and sufficient condition for being acyclic. And we're going to take advantage of that to kind of describe a structure for general digraphs for connectivity purposes. And that's the content of this next proposition. So I'm going to start with the digraph D, and what we're going to do is we're going to look at all the strong components, and then for each strong component, we're going to identify it to a single vertex. And then what we're going to show is that digraph that we obtain after that identification. So when you identify all those vertices to a single node, you throw out all the edges with both ends in that set. That new digraph is going to be acyclic. So again, D is a digraph. D prime is obtained from D by identifying every strong component of D to a single vertex. And then deleting loops. And then the statement is that this digraph D prime is going to be acyclic. And there's very little to the proof here. What have we done? We've taken a digraph and we have identified all of the strong components to single vertices. Now, could it be that this new digraph that we form suddenly has a directed cycle? Let's look at this picture. So maybe these were all strong components of our digraph, and after identifying them, we have a cycle. In fact, maybe what I should do, let me draw this a little bit differently. I'm mostly just going to draw the picture. I mean, this is really very, very immediate. So if you saw a cycle, a directed cycle, here in D prime, then in the original digraph D, each of those vertices would be a strong component. Right? What that means is that you have some edges like this between these strong components. But now this has gone silly. Because what? Well, because you have strong components, right? Because these are strong components, I can walk from this vertex to this one within this strong component. I can walk from this vertex to this vertex within this strong component. And same thing down here, and same thing here, and same thing here. Right? So because I can walk from each of these, so for each of these strong components, sorry, let me back up. So in D prime, we saw a cycle, a directed cycle. When you look at those edges in the original digraph, what do you see? Well, for each of those strong components in D that corresponds to a vertex in D prime, one of the edges of that directed cycle that we saw in D prime is going to be directed in, and one's going to be directed out. Because you have a strong component, you can find a directed walk from the one that's coming in to the one that's coming out. That's when you put all of those things together, you're getting a giant closed walk in the original digraph that is that's telling you that all of the vertices in all of these components that all the vertices within this closed directed walk have to be in the same strong component, and that's contradicting our assumption, right? So our assumption was that these things were all strong components, and and that just can't be, because every vertex is in a unique strong component, and any time you see a closed walk, all the vertices and all the edges in that closed walk have to be part of the same strong component. So we get a contradiction to our basic assumptions. So I'm not going to write anything much here. So if D prime has a cycle, by which I mean directed cycle, then D has a directed closed walk that's not in any strong component, and this is a contradiction. And so that means that D prime cannot have a directed cycle, and if D prime does not have a directed cycle, then it's acyclic, and that is that's what we're aiming to prove. So now what I want to do is I want to just sort of put together this proposition together with the together with our understanding of strong components. So what are we saying now? So if I give you any digraph D, they're strong components. Those strong components, so they're strongly connected subdigraphs. Those strong components are going to give us a partition of the vertex set of the original graph. I mean, maybe just one, but whatever. It's going to give us a partition of the vertex set of the original graph. So every vertex is in a unique strong component. Now, what this last proposition is telling us is if you take each of those strong components and just identify it to a vertex, so each strong component is just getting crushed to a vertex, and delete the loops that you form when you do that, then that digraph is acyclic. So what that means is that digraph is going to have an ordering. You can order the vertices left to right so that all of the edges go strictly left to right. And that's an easy way of seeing that you don't have any directed cycle in that resulting digraph. And this is kind of all that we're going to do for the kind of connectivity structure of general digraphs. So again, we're not coming up with one simple structure that encodes exactly when there is a directed walk from any vertex U to any vertex V in a digraph. We're just not doing that. We're giving a kind of good structure that illuminates a lot of this connectivity, but not all. So let me just draw a kind of just a quick picture here. So again, this is going to be a structure that you can find in every digraph D. So in every digraph D that you have, you're going to have some number of strong components. Your graph is going to have the feature that when you look at the partition of your vertices into strong components, those strong components can be ordered in linearly, left to right, in such a way that all of the edges that are not part of a strong component go left to right in the picture, right? So what we're saying here is that I'm not really telling you exactly when these edges are going to be present and when they won't be. That's really a more complicated thing. But what I am telling you is that all of the edges that are not within one of the strong components here will be directed left to right. So maybe our digraph looks like this. And again, this is what we're coming to as our kind of structure for connectivity in a digraph. This is kind of the best we can do. So again, anytime I'm giving you a digraph, you can form the strong components. The last couple of lemmas that we've proved are telling you that in fact you can then take those strong components and you can find a left to right ordering of the strong components so that every edge that's not contained in one of the strong components will be oriented left to right relative to this ordering. And so you can see then, if I give you two vertices that are in the same strong component, well, you're going to have a directed walk from this one to that one and from that one to this one. If I give you two vertices that are not in the same strong component, then you're going to know something one way. So if I give you a vertex that's in a later strong component and a vertex that's in an earlier one, right? Well, all the edges are directed this way within our within our picture. So that means you can't get from the later one to the earlier one. You might or might not be able to get from the earlier one to the later one. So there is a little bit more to this story, but this is what we're going to take as our structure. And this structure is very good at kind of making it clear that you got your strong components correct. And it's a very useful picture for a digraph. And that's what we've got. So we've got one more lemma that I'd like to prove about about strong connectivity. This is a nice one. Oh, it's called a theorem in the notes. I'll call it a theorem. This tells us if I give you a graph G that is too connected, then you can find an orientation of G that is strongly connected. So this is a totally different looking game, right? I'm giving you an undirected graph, and I want to find an orientation of that undirected graph that is strongly connected. And anyway, and our theorem is going to tell us that 2 connectivity is enough for that. There is an orientation of G that is, let me give it a name, orientation D of G that is strongly connected. So that's a nice fact. So if I give you, strong connectivity is a thing we like. We like things that are connected. At least if I gave you a graph G that's too connected, then you can choose a strong orientation of the thing. And the proof of this is a pretty easy one. Again, when I give you a too connected graph, we know that you have this this nice ear removal property. You can, if you want, you can go all the way back to the bottom and think of it as an ear decomposition. I'm just going to do one step. So, so I'm going to do induction on the number of vertices. Let's say, as a base case, if you have one vertex, then you're already done because any one vertex graph is strongly connected. For the inductive step, I'm now going to ask, is C actually a cycle? If C is a cycle, then we orient it to be a directed cycle. Right, that's easy enough. Of course, this is a thing we can do. The directed cycle already comes kind of with an ordering of the vertices, right? A cycle already comes kind of with an implicit ordering of the vertices. Your graph is a cycle if there exists an ordering v1, v2 on up to vn, so that blah, blah, blah. Just take that same thing and orient the edges, and you've got a directed cycle. It's immediate that a directed cycle is strongly connected, so that's good. So we're done in that case. Otherwise, I should have said, let's do. Sorry, let's do induction on vertices plus edges. I have to be I have to be a little bit careful because the operation I want to do, of course, is remove an ear, and if I'm not suitably careful, I might be removing an ear that's. If I want to do that, I have to be prepared that I might just remove a single edge, and so I want that to be decreasing my inductive parameter. So I'm just sort of casually going by induction on number of vertices plus number of edges. If I do that, I'm allowed to do induction on it, certainly. The base case still works. If you've got just one, that's going to be one vertex and no edges, and the theorem holds. Now for the inductive step, again, if you have a cycle C, I'm going to orient it to be a directed cycle. Otherwise, I can choose an ear that can be removed. and so we'll remove it. Each E has a removable ear. Let's call it P. Now, the graph obtained from G by removing P, I'll call G prime. So now G prime is a two-connected graph, and it has fewer edges plus vertices than the graph G. So by induction, G prime has a strongly connected orientation. Let's give that strongly connected orientation a name. Let's call that strongly connected orientation D prime. And let me try and draw a picture here. So, okay. So here's D prime. This is again, the orientation of G prime. And we removed an ear, say P. I'm going to do what's probably looking like the natural thing to do from here. Let's say P. Let's say the P has ends. Let me name the ends of P. Let's say here with ends. The ends of the path will be U and V. So I'll give names to these. There's vertex U and there's vertex V. Now, again, so we've found a nice orientation of G prime, of the smaller of this subgraph G prime. We did that by induction. D prime is now a strongly connected digraph. Now, of course, I want to orient not just what was in G prime, but also the rest of the edges, namely these edges in P. We have to give those an orientation to complete to get what we want, and we're going to orient them kind of in the obvious way. We're going to orient it to make it a directed path. So now what we're going to do is we're going to orient P to be a directed path from U to V, thus forming an orientation D of the original graph G, and call this orientation of G. Call this orientation D. Okay, so right, let me add this to my picture. So I've oriented this path P so that it's a directed path from U to V, and now I'm going to claim that this is a strongly connected orientation of the original graph. So I'm claiming that this digraph D is strongly connected. And the proof of this is very easy. My digraph D prime is strongly connected. So D prime has a directed walk from V back to U. So since D prime is strongly connected, it has a directed walk from U to V. Oh, sorry, from V to U. Right? Now, the presence of this directed walk from V to U, that means that all the vertices in my whole path P, all the vertices in that path have got to be in the same strong component of D. Why? Well, I just have a little directed path out here. Certainly you can walk from any vertex that's earlier on the path to any vertex that's later on the path, but you have one that's later on the path, then you can follow along this directed walk in G prime from V to U and then reach any of the earlier ones. So it follows from the presence of this directed walk that all vertices of P must be in the same strong component. On the other hand, U and V must be in the same strong component as all of the rest of the vertices of G prime, because G prime because D prime is strongly connected, right? So D prime, all of the vertices in D prime, which are the same as the vertices in G prime, they are all part of the same strong component. So this implies, let's say this implies that all of V of P in same strong component. And this implies that D is strongly connected, thus completing our proof. So if I give you a digraph that's too connected and you're allowed to choose an orientation of it, then you can choose an orientation which is strongly connected. Of course, it's very easy to choose orientations that are not strongly connected. I can choose an orientation that's acyclic very easily. Take the vertices and order them however, you can orient the edges left to right and you just get an acyclic digraph, which is kind of the other extreme. But that's quite trivial. Much more interesting here is that when you have a digraph that is too connected, then you can orient it in such a way that that you get a strongly connected digraph. And that'll complete this section on connectivity of digraphs.